Hello everyone, Ross Satchell from Microchip Technology again. Today we're taking a look at the zero crossing detector peripheral in the Avr DA. The Avr DA family of MCUs has a new feature not previously seen in AVRs, the zero crossing detector, or ZCD. So what is a ZCD and why would I want one? Traditional ZCDs have been around for a long time and are used to detect when an AC signal, which is often mains voltage, crosses the 0 volt threshold. It can be used as a frequency counter, accurate long-term time measurement, or for dimming or switching in power electronics circuits. It also finds applications in detecting the presence of mains voltages as part of low-cost safety switches. If they've been around for a long time, why is this one better? MCU I/O pins have electrostatic discharge or ESD protection structures that behave like diodes. Normally, these are used to shunt ESD to either VDD or ground. Traditionally, the commonly accepted practice was to utilize these ESD protection diodes and insert a large series current limiting resistor to allow detection of the presence of high voltage. This worked and the microcontroller connected was not damaged even when thousands of volts were present at the current limiting resistor. However, there were some undesirable side effects produced. When AC and particularly negative voltages were used, the current flowing through the series resistor was routed by the protection diodes through the silicon substrate and down to ground. This could result in some fairly minor issues such as an offset to ADC readings or affecting the accuracy of a voltage reference due to shifting either the VDD or ground potentials. However, it could also result in the disruption of a low power oscillator or even trigger a brownout reset condition. Unfortunately, today this is no longer possible, as the resulting injected current into the substrate cannot be tolerated well by devices manufactured using more modern process technologies. In order to protect the MCUs now, requires the use of capacitors, Zener and Schottky diodes for each input, which substantially increases the bill of materials or BOM cost of the project. The ZCD in the Avr DA family of devices overcomes this problem by using the idea of keeping the input pin at precisely one specific voltage, which is the zero crossing reference voltage. More on that later. Rather than just within the normal voltage range. This is achieved by comparing the input voltage to an internal reference and then driving one of two current sources. When the external AC voltage is above the zero cross reference voltage, the low side current source is activated to draw current into the device, which produces a voltage drop across the series resistor and counteracts its effect. Then when the input voltage is below the zero cross reference voltage, the high side current source is activated, which sources current out of the device and produces an opposite voltage drop. The series resistor value must be calculated correctly so that a small peak current of about 300 microamps is able to counter typical mains voltages of 110 to 240 volts. So now the problem has been reduced to identifying the moment when the two current sources are being switched. This is achieved by detecting when the current through the ZCD input pin changes direction. It's important to note that the zero cross reference voltage is not actually 0 volts, it's about 0.8 volts. If it's a zero crossing detector, why is it detecting at about 0.8 volts? It would make the Avr DA much more expensive and have much higher power consumption to have a ZCD that detects at exactly 0 volts. As a result, 0.8 volts is about as low as the process technology allows without introducing charge pumps, which are expensive and consume far more current. Since the input voltage is likely to be mains power ranging from 110 to 240 volts, that 0.8 volt zero crossing point is negligible for most applications. Having the zero crossing reference at about 0.8 volts introduces a small phase shift. However, since we are able to measure the input frequency and we know the voltage offset, we can use a timer to determine the moment when the true zero crossing occurs. For applications with a sinusoidal input voltage, the input can be corrected by AC coupling, using a capacitor in series with the current limiting resistor, or having a pull-up or pull-down resistor to compensate the voltage offset. The ZCD module also includes a status bit to determine when the current source or sink is active, so we can easily determine whether the input signal is currently positive or negative. As the input signal crosses the zero crossing reference, the output toggles, resulting in a square wave with a period equal to that of the input signal. The Zcd output can be used externally as a digital output or internally with other peripherals. Additionally, the Zcd peripheral can be used to trigger events or interrupts on rising edges, falling edges, or both, and the polarity of the output can even be inverted. The Zcd peripheral is a core independent peripheral, or CIP, meaning that once it is set up, it doesn't require any CPU intervention at all, meaning that the CPU can be sleeping and only waking when necessary, which makes it very valuable in low-power applications. The Avr DA, depending on the package selected, can have up to 3 zero-cross detectors. So, the Zcd peripheral on the Avr DA family of devices can help substantially reduce the BOM cost and power consumption of your next project, while eliminating the known shortcomings of the traditional method of zero-crossing detection. For more information, check out the links in the description below. Remember to smash that subscribe button and hit that notification bell to get the newest content from Microchip Technology. If you enjoyed this video, please give it a like or a comment. Thanks for watching.